Hello everyone, this is Humza Akhtar 10870, team lead of Group 13. Today I'm here to present to you the algorithm that we chose for our project, which is the Quake III's algorithm, also known as Quake's fast inverse square root algorithm. In this video, I will be discussing the introduction to the Quake III's algorithm, as in what it is, the need for it, and its working. Furthermore, we will look into the code and break down the algorithm and look at its time complexity, best and worst cases. Moving on, we will take two real-life examples of Quake III and then discuss what our testing for the algorithm was and what results we got, and lastly, the conclusion and our views on this magical algorithm known as the Quake III's algorithm. Speaking about the introduction first, now I'm pretty sure you all must have heard of 3D graphics and physics simulations. The Quake 3 algorithm, being a fast and efficient method, is used for computing the inverse square root of a number, which is essential for various vector calculations, further helping in optimizing the overall speed. Okay, so now talking about the need of quick algorithm, I'm pretty sure that the first question coming in all of your mind must be that why would the game engine want to calculate 1 divided by square root of x? So the answer for this is if you want to implement physics or lightning or reflections in your game engine, it helps if the vectors you're calculating with are normalized to length 1 because otherwise your vectors might be too short or too long, and when you do physics with them, things can go wrong. Okay, so now we will be discussing the logics that explain that why is there a need for Quake III's algorithm. As all of you know that the length of a vector is square root of x squared plus y squared plus z squared, which is basically the Pythagoras theorem. So if we want to normalize the vector's length to 1, we have to scale everything down by the length of the vector, because if we divide the length of the vector by the length of the vector, we obviously get 1. Now, if we talk about calculating x squared plus y squared plus z squared, it is really easy and most importantly really fast in code, because if you want to implement it, you can just do it as x times x plus y times y plus z times z, and all these are just three multiplications and additions summed up. But the square root, on the other hand, is terribly slow operation, and division is not much better. This is not good if we have several thousands of surfaces where each has a vector that needs to be normalized. But on the bright side, this means that here we have an opportunity for speed improvements, and if we can find just an approximation of 1 divided by square root of x, as long as it's fast, we can save precious time. Hence, we can say that the fast inverse square root is such an approximation with only an error of at most 1% while being 3 times as fast. Now moving on to the past, where the algorithm was first introduced. Well, the Quick Trees algorithm was first introduced and developed by ID Software and released in 1999. In 2005, a game company open-sourced the engine for their video game called Quake III Arena. In that source code, fans of the game discovered an algorithm that was so ingenious it quickly became famous, and the only thing that this algorithm does is calculate the inverse square root. Okay, so now we will be discussing the working and methodology of Quake III's algorithm. In order to understand this, we have to dive into the application, as in where the algorithm is originally used. So when we talk about developing games, making the game more and more efficient is the first thing that comes in our mind. The faster a game can perform calculations and render graphic, the smoother and more immersive the gameplay experience becomes. One game that pushed the boundaries of performance optimization is Quake III Arena, which introduced an algorithm known as the Quake III algorithm. This algorithm, designed to compute the inverse square root of a number, played a crucial role in the game's physics engine and lightning calculations. In the realm of physics simulation, in order to achieve accurate lightning and reflection calculations, normalization of vector is necessary. This ensures that the game's graphics accurately depict depth and shadows, providing a more realistic and immersive experience for players. Just like how we discussed in the previous slide, that how the vectors must be of length 1, also known as a unit vector, and how the calculating the inverse square root in real time can be computationally expensive for CPUs, especially when dealing with large number of calculations per second. This is where the Quake III's algorithm comes into play, offering a faster alternative for computing the inverse square root. Now checking out the code of the algorithm, if I had to write a piece of code that would calculate the inverse of a square root, this is how I would do it. You can see on the bottom left corner of the slide, here I'm using the C programming language, the same programming language used for Quake 3. On the top right corner, you can see the Quick Three's algorithm. At first glance, it doesn't seem to make any sense. Where does this constant number come from? What does this have to do with taking roots? And why is there a disgusting curse in the second comment? But but we're gonna take a look at the code and see that how with some cool bit manipulation you can take in square roots, and the algorithm that does all of this bears the name as Quick Three's algorithm. Now looking at the code again, we can see that the beginning is pretty harmless. We are given a number called number as input, the number we are supposed to take this inverse square root of. First, with the variable I, we declare a 32-bit number. Then we declare two 32-bit decimal numbers, x2 and y, and then we store 1.5 into the variable with the obvious name called 3 halves. The next two lines simply copy half of the input into x2 and the whole input into y, but it's after that where the magic actually happens. Take a moment to look at it again. Well, the longer you look at it, the less sense it makes, and the comments on the right are not helpful either. But they do hint that there are three steps to this algorithm, puzzling together that these three steps will show us the brilliancy of this algorithm. The first step in the Quick Threes algorithm involves a bit of evil floating point bit level hacking. The algorithm takes the floating point number and stores it in the variable y and interprets the bits of y as a 32-bit integer using a bit level cast. This allows manipulation of the bits representing the floating point number. The next step introduces a mysterious constant that you can see in the code, often referred to the magic number. This value is subtracted from the right-shifted integer I. The purpose of this subtraction is to approximate the inverse square root of the original number. We will discuss the magic behind this when we are done discussing the rest of the code. After obtaining the initial approximation of the inverse square root, the algorithm applies one iteration of After obtaining the initial approximation of the inverse square root, the algorithm applies one iteration of Newton's method to refine the estimate. This iteration involves multiplying the approximation by 3 halves and subtracting x2 into y. The result is a more precise approximation of the inverse square root. Finally, the refined approximation is returned as a result of the function. Now discussing what the magic behind the number constant is, well, it minimizes the error in the approximation for both odd and even exponents, ensuring accuracy in a wide range of scenarios. Talking about how the selection of this particular constant was done, well, it is not arbitrary, but rather based on result of careful optimization, hence achieving its computational efficiency without the need for square root operations. Now that we are done discussing the original algorithm, the pseudocode that we came up is shown right here. Now that we are done discussing the original algorithm, the pseudocode that we came up with is shown right here. First, talking about the initialization of variables, as you can see in the line x2 equals number into 0. 0.5, it calculates the half of the input number. The second line, y equals number, it initializes y to the input number. The third line, 3 halves equals 1.5, it is a constant used in the algorithm. Just how we discussed in the original algo, the bit level hacking is done here as well. As you can see in the line I equals cast float to int y, it converts the floating point number y to an integer I. This is a form of bit level manipulation. As you can see in the line after that, I equals 0x5f3759df minus I greater than 1. This line applies a bitwise shift and subtraction to I. It involves the magic number manipulation specific to this algorithm. It is a key step that contributes to the speed of the algorithm. The line after that, that is y equals cast into float I, converts the modified integer I back to the floating point number y. In the line after that, you can see that the first iteration of Newton-Raphson method, which all of you must know is a numerical method. For those who don't, it is like a root-finding algorithm considered the most fastest in all the iterative ones, being the core mathematical operation in this algorithm. The line y equals y into 3 halves minus x2 into y, this line performs the first iteration of Newton-Raphson method for approximating the inverse square root. The return y line returns the result which approximate the inverse square root of the input number. The following slides just explain what I just did in the previous ones. It just gives a detailed explanation of the pseudocode that we presented in this presentation. Breaking down the algorithm further and calculating its time complexity as shown in the Algo, the first inverse square root algorithm primarily involves a fixed number of operations regardless of the input value. Therefore, we can consider the time complexity as constant or O of 1. Speaking of the upper and lower bound, that is the best and worst cases of the Quake III algorithm, well the fast inverse square root algorithm is not typically analyzed in terms of best and worst cases in the traditional sense because its primary purpose is speed optimization rather than achieving the utmost precision. But still, if we talk about the best case, that is the lower bound of the algorithm, based on the time complexity perspective, it is constant, that is O of 1, as it performs the same set of fixed operations regardless of the input value. Similar to the best case, the upper bound, that is the worst time complexity, is same as constant, that is O of 1, because the number of operations remains the same. Now talking about the real-world applications and the examples of the Quake III's algorithm, first one being COD and Battlefield series. The Call of Duty and Battlefield game series incorporate advanced rendering techniques inspired by concepts like those found in Quake III's algorithm. However, the one thing that should be kept in mind is rendering is very crucial in these games. Algorithms are employed to quickly identify and render only the portions of the environment visible from the player's viewpoint. This approach ensures that the game engine processes and displays only what's necessary, optimizing performance without compromising visual quality. The final aim is to provide players with an immersive gaming experience, ensuring smooth gameplay even in multiplayer modes with numerous players interacting simultaneously. Speaking of the second application of the Quick 3's algorithm, being virtual and augmented reality, that is VR and AR, VR and AR applications integrate spatial partitioning techniques to efficiently manage and process complex 3D environments. From the Quick Trees algorithm, these applications, just like COD, utilize rapid visibility determination algorithm. These algorithms render only the elements within the user's field of view by focusing solely on visible components without compromising visual quality and helps in reducing unnecessary computations and enabling smooth, responsive interactions, contributing significantly to an engaging experience. In the testing and results phase of our research, we tested the accuracy of Quick's fast inverse square root by performing a couple of steps. The first one being the translation of the code into Python using NumPy. Then a new function called TrueValue was coded to calculate the true inverse square root value, and then a random float number was generated and its inverse square root was computed using both the Quick's function and the TrueValue function. After computing both the values as well, the difference between the two were stored in an array which was done inside a loop to generate results for 5 random float numbers. As you can see here, the converted Python code of the Quick Trees algorithm is shown on the background of the slide. In accordance with the snippet of the result, you can see that the quick estimate and the true value for the 5 random numbers have a difference of 2 into 0.01, making quick function accurate to only 2 decimal places. Ending the video that you were watching with such focus, I would just say that how personally I found this topic very interesting, even though this wasn't made by solely one person, but instead several through open source work and collaboration. It can show how even a simple problem can be tackled and optimized to insane levels for the sake of efficiency or convenience for programmers. In accordance to our research, we can say that the algorithm demonstrated is a clever use of bit manipulation and exploits the floating point representation in the IEEE 754 standard, being a notable algorithm which efficiently calculates the reciprocal square root, which is a crucial operation for 3D graphics rendering. Thank you for watching the video. You can check the project report and the presentation both in the description box below.